Hello everyone, I'm Jing Wang from Capital Normal University, China. It's my pleasure to present our work, Enabling Energy-Efficient and Reliable Neural Network via Neuron-Level Voltage Scaling. I'd like to show my presentation in 5 parts. Deeper neural networks with more parameters greatly enhance the output accuracy. However, complex neural networks would incur heavy computation and intensive memory accesses, leading to extremely high power consumption. Voltage scaling is a promising technique that enables power saving. Nevertheless, it will induce errors, causing the network output accuracy to fall below users' requirements, and induce frequency degradation, causing excessive delay and a significant drop in performance. However, neurons in the neural networks usually exhibit different fault tolerance capabilities. As the figure shows, the blue, yellow, and red colors represent the lowest, middle, and highest voltage levels in the system respectively. The neuron size described its resilience to the voltage scaling-induced errors. A smaller size means a stronger fault tolerance capability. When randomly selecting neurons for voltage scaling, a car may be misclassified as a bike. On the contrary, when intelligently selecting more resilient neurons for voltage scaling, for example, applying the lowest voltage with the blue color to the most resilient neurons with the smallest size, the car is still correctly classified with tremendous power saving. This motivates us to conduct fine-grained voltage scaling at a neuron level, which leverages the difference in neural resilience for optimal energy efficiency and reliability. We propose a comprehensive neural network characterization framework called NNAP. NNAP models the output accuracy loss A, power saving P, and performance degradation of neural networks NN for a given voltage level at the neural granularity. Then the framework will be used to guide neuron level voltage scaling. And we also propose neuron clustering and mapping schemes to minimize voltage regulators overhead and achieve load balancing. First is the accuracy model. It is well known that errors will propagate across layers in the network, and how to quantify the accuracy loss caused by voltage scaling-induced errors is a key challenge. Based on the Taylor expansion approach, we present a theoretical fault tolerance capability analysis and identify errors accumulated in the intra-layers and multiplied in the inter-layers. We define a metric, effect factor of accuracy, EFOA, to link voltage and neural robustness to the output accuracy loss. EFOA is the product of the gradient and error rate. Gradient is getting from backpropagation, and error rate varies with voltage. Power consumption is divided into 2 parts, the computation power and memory access power. The computation power can be described as the total power cost of addition and multiplication operations per clock cycle. Memory access cost is the power cost per bit multiplied by the total number of bits. We formulate the calculation of the accumulation, multiplication, and memory access number for each type of layers as shown in the table. For the performance model, we use the minimum delay of the neural network to represent performance. Neurons of one layer may not execute at the same time because of the limited hardware resources. The process elements should be used iteratively. We call each use of all on-chip process elements as a run. For each run, the lowest voltage of the neurons in the workload will determine the maximum delay. The delay of the ith layer is the sum of the maximum delays of each run. Because the network will execute sequentially, the total delay is the accumulation of the maximum delay of each layer. To satisfy different users' requirements for neural network across different application domains, we propose to use the NNAP framework as a guidance to identify the optimal voltage solution. There are multiple aspects such as accuracy, power, and performance are needed to be considered. So we model voltage scaling as multi-objective optimization problems. We conduct 3 case studies: low power, high accuracy, and high performance. Take the low power case as an example. The objective function is to maximize power saving, while the constraints are total accuracy loss is smaller than EFOA budget and the delay overhead is smaller than delay budget. Assigning voltage at the neuron level requires many voltage regulators, inducing substantially high area and transition energy overheads. To minimize the number of required voltage regulators, we use the clustering method to build multiple voltage islands, which applies the same voltage to neurons with similar fault tolerance capabilities. The centers of the clusters will be used as the final voltage. After determining each cluster's voltage, the next step is to allocate neurons to precise elements. The number of cores may not fit the number of clusters, and the number of precise elements in each core may not match the number of neurons in each cluster. Hence, to solve the load balanced problem caused by the allocation of cores, we extend the knapsack problem. Each round of the knapsack process identifies how many clusters of the former ith clusters could be executed simultaneously and determines whether running the ith cluster or not in this run achieves higher system utility. Through multiple rounds of knapsack processes, we can determine how many runs of execution are needed for one layer, as well as the cluster type and the number for each iteration. For example, a cluster set such as this ran on hardware with a capacity of 5. NN-app mapping reduced 1 run compared with the sequential scheme. In our experiment, we define a metric M-app to quantify the trade-off between accuracy, power, and performance. A higher M-app indicates better user satisfaction. Take a low-power target as an example. The NN-app scheme can achieve at most approximately 16 times M-app gains compared with random voltage scaling. Detailed analysis shows that the main gain of M-app comes from delays. This is because under the same delay budget, the difference between the highest and the lowest voltages of the random scheme is usually larger than that obtained with NN-app. In summary, the NN-app scheme can achieve approximately 16 times, 5 times, 1.7 times, 2 times M-app gains on different datasets at low power target case. Finally, I give the following conclusion. We developed the NN-app to comprehensively characterize neural networks from different perspectives, including accuracy, power, and performance. Especially considering the error robustness varies across neurons, we analyze the error propagation in neural networks at both inter- and intra-network layers to precisely model the impact of voltage scaling on the final output accuracy at neuron level. We propose multi-objective optimization for neural networks via fine-grained neuron-level voltage scaling based on NN-app. The clustering and mapping scheme minimize implementation overhead and achieve load balancing. The experiment results show that NN-app provides guidance for achieving future energy-efficient and reliable neural networks configurations under given constraints, thus maximizing user satisfaction. That's all. Thank you for your attention.